Hi, my name is Julia Sully, and I'm a data scientist and software engineer at our studio. And today, in this screencast, we are going to use data from the TV show Avatar: The Last Airbender, and we are going to train a model to predict who the speaker is for individual lines from the television show. And we are going to train a couple kinds of models, see which one, how they do, and then we're going to talk about how to compute variable importance using permutation.
Hello, welcome. Let's get started. Today we are dealing with a really fun data set about a TV show, Avatar: The Last Airbender. And this show is so fun, actually, that I think I'm going to make all my plots themed so that all my plots can look like they belong to the show. This is actually a pretty popular show here at my house. Slayer, and my kids like it, and I like it. Although I will admit they've watched more of it than I have. So this is a great and fun package that can make our fonts look have themes from different TV shows, and fortunately we have one here right from Avatar: The Last Airbender. So here is the data set of what we have. So if we take a look at it, we have one row per every line of either dialogue, or so the dialogue is repeated here in both the character words column and the full text column here. So sometimes it is words spoken by a character, and sometimes over here it is a different kind of text. We can see that it is sometimes scene description. So there's a lot of different kinds of analysis we could do here, and there's so much fun analysis and visualization happening in the Tidy Tuesday community. There's this rating over here. There's actually, if we look here and look at like how many actually so the seasons are called books. There's these three seasons, these three books: Earth, Water, Water, Earth, and Fire. And then there's chapters, which are the episodes. So there's 61 episodes, and so that is what is linked up with the directors and the IMDb ratings. So if I wanted to do some modeling, that is just not very much data, and I would really like to be able to demonstrate some modeling and machine learning using this data set. So that, I'm afraid, is just not going to do it, like 61 episodes. On the other hand, we do have all of these lines, these spoken these spoken lines spoken by characters, and or these this scene direction. So what we're going to do here is give a go at taking the spoken dialogue and seeing what we can do in terms of connecting the spoken dialogue, like Katara, settle down, and see who speaks it. In this case, it is Sokka. So we're going to see if we can predict who is speaking from what is being spoken here. So we're going to try to build a model to do that. So let's see who the most common speakers are here. So the scene description is, as we might expect, the most common, and behind that comes Aang. So Aang is the main character, the the Last Airbender, if you will. And then we have his friends, Sokka, Katara, and Zuko. Tofu comes in later, and some of these other other characters who he meets during the course of what goes on in the story. What I would like to see if I can do is build a model to identify if a line of dialogue is spoken by Aang or someone else. So I think that is what I would like to try to see if I can build a model to do. So let's start out by doing a bit of exploration. First, let's look over the course of the 3 seasons, the 3 chapters. 3 books, excuse me, chapters or episodes. Let's see what we see here. So first, I'm not going to look at the I am not character words. I am not going to look at the scene description. I'm only going to look at the spoken dialogue. And let's look at the let's make this into a factor, the book, in order that we see it here. So the water will come first. And let's see what the most common characters are, so we can get an idea of who we are who we are going to be lumping together. So we can do these like lump low frequency. I'm going to make a plot, so I'm going to lump N together. So I'm going to lump the character variable together, and I only want 10 to get here. And then let's count book character like so, and make a plot. So I'm going to put N on the x-axis, character on the y-axis, and make fill equals to book. And I'm going to make use geom call. And let's facet wrap by book. And let's do scales equals free, like here. All right, so you can tell that we have our beautiful fonts and some of our theme here for the show, which is great. So we don't need that y-axis, and let us let's make this in order. Let's order this a little bit so we can tell what's going on. So after we count, let's mutate. Let's say character, and let's use this function from tidytext called reorder within. So we will reorder character by and within book, like that. And then what we have to do after that, we have to add a scale y reordered like this. So this will reorder it like so. So that's looking good. And now those colors are not avatar colors. So let's try to make some avatar colors here. There are people, if you explore the Tidy Tuesday, people who are involved in Tidy Tuesday, there's going to be much more amazing visualizations than what I'm doing here. But I'm going to. So there's a function called avatar palette here that you can get some of these palettes out. And so the way that this works is you give it, so the palettes work, you give the name of the palette and then you put in an N. So we want, for this plot here, we want three of the different palettes. So we want Water Tribe. And the way these palette, whoops, I didn't even put in palette. Whoopsie daisy. Okay, so avatar palette. So the Water Tribe, like that, and then you put the one after it, like that. Like you're saying you just want one. So if I do that, we need 3 of them, right? So I only did 1. So if we go like this, and we do 2, 3, like this, and we only want one color from each of these. So we let's see, plots. So we have water, earth, and then fire. So we need Earth Kingdom and Fire Nation, like so. And so that looks pretty good. That first color, it'd be nicer if it was red rather than yellow, but that's okay. Okay, so this is how many lines are spoken by these characters in the 3 books. So, you know, perhaps unsurprisingly, when you bin a whole bunch of other together, that is very common, you know, lots. But other than other, Aang speaks the most in water. And then Katara is right behind Aang. Sokka actually speaks the most, more than Aang actually, in Earth and Fire, which is pretty interesting. And Sokka is behind Aang, and which I guess makes sense. So we can see these. How often do these different characters speak? And so what we're gonna make an attempt to do here is to identify from their from a line of dialogue, is the speaker Aang or is the speaker someone else? So let's build a little data frame to do this with. So let's take our raw data frame. So we do not want any of those rows that have the scene direction. Let's make a column called Aang, which we'll just use if else. So when the character is equal to Aang, it is Aang, and else it is other, like this. And then let's take that new variable we just made. Let's take book in case we need it. I'm not sure if we will. And then let's take the character words like so. Then let's call this avatar. So this is a data frame that we're going to use for a few things. And let's just look at a few, just to kind of get an idea of what we might be trying to get ourselves in for here. So for some lines spoken by Aang, let's just take a few and pull them out, pull text like this, and let's just see what we're getting. Size, filter, I did never do it. There we go. What am I doing? Avatar is here. Filter Aang is equal to, whoops, there we go. Okay, let's try again. Okay. Hi, I'm Aang. Okay, some of these are so short. Oh boy, this is going to be, I don't know if this is going to work at all. Let's, all right, I did do a little exploration ahead of time. Okay, so here's Aang talking to his friends. Okay, so there is a fair amount of data here, but these are so short. This is an amazing data set. It is super fun. But these are so short. So notice how short these are. Notice and just think about looking at this, like how hard would it be for you as a human being to tell whether this was spoken by Aang or by one of the other characters. You know, if you are someone who knows the show, even if you're someone who knows the show, how hard would it be for you to do this? So this is what this is what I've decided to try to make a screencast to do. So we'll see if this is a terrible idea or not. Here, okay. Before we move any further, let's do a couple more things. So let's convert. So this right now, the strings are all, stored in a column called text. And let's tidy this, make this into a tidy text format. So we will tidy into Word from text like this. And let's count for the Aang versus other, what the words are. So now this, you know, so we have Aang saying ah and ah and ah, and Aang saying Aang. And then let's load a function called, or load a package called tidylo. Tidylo is a package for weighted log odds using tidy data principles. And we can use a function called bind log odds. And we say, first we say the set, and then we use the feature and then the counts like this. And it will compute the weighted log odds. You can look in the documentation for more details about the kinds of weightings that are available there. But we can, for example, now arrange by this weighted log odds, find out what are the highest weighted log odds. So this is for, so Aang, you know, talking to Katara, saying I. So Aang is much more likely to say I and I'm than the other characters. Aang is more likely to say Momo. Other characters are more likely to say welcome. So let's call this avatar log odds. And then let's make a little bit of a visualization. I do want to notice how low these counts are. Well, this is a fair amount of data, like thousands of rows. But as we look at this, let's take the top 15, or we can use slice if we want. Slice max, I think. So slice max by log odds weighted, and n equals 15, I believe. No. Oh yeah. Well, I have to make it first. Okay, so this is now the top 15 in both groups. And let's reorder those. So word reorder, word log odds weighted. And then let's make a plot. So let's put the weighted log odds on the x-axis, word on the y-axis, and whether it is Aang or not as the fill. Let's use a bar chart again. And let's facet wrap so that we have Aang and other next to each other, like so. All right, good. So we don't need that Y label. And this time, let's use scale fill avatar like this. And so this, I believe, is the Fire. Yeah, this is the Fire Nation, but we can use. Let's use. So this is Aang, and let's use. Let's use the Air Nomads. Since nice. Okay. So these are the words that have the highest log odds of being spoken by Aang versus everyone else. So Aang is more likely to, say the name of Sokka and Katara and Appa, yip, 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 as he speaks his bison thing. And the other people are more likely to say mother, princess, prison, men, escape, things like that. Aang is less likely to say these words. So one option when it comes to trying to build kind of text model is to do it from the content of the words itself. And there is information in the words, that's what we're looking at when we look at this, plot. However, I will suggest that we don't have enough data to, or it's going to be hard. It's going to be tough to build a model with the amount of data that we have from this. We could certainly give it a go, but we saw what the counts were here on this. So like we would be building a model where the counts were things like this. Like the counts on our features would be things like this. So instead, I want to show another option that sometimes can work when you have text, and that is to look at other kinds of features in the words. And there's a nice package for doing this that's called text features. And let's walk through how to create these, just using the package in its basic form, and then how we can do it using tidymodels so it's ready for modeling. So the kind of features that we're talking about are not the words, but instead features of the text, like what are the number of characters per word? How many punctuation marks are there? How many spaces are there per document, and things like that. So these are features of the text that are not connected to the actual vocabulary of the text itself. So let's talk about how to do that. So we'll load the text features package, and then we'll use this text features function. We can give it the data frame we have because it has a column called text, and then we will say we're not going to do the sentiment scores, and we are not going to do word vectors here. And also I'm just turn off a bunch of these things. We're not going to normalize it because we're actually going to do that within tidymodels later. So if we do this, it's now counting up the features in the text. It finds the parts of speech and whatnot. And what we get here now is a new tibble. It has the same number of rows as our old tibble. Notice it doesn't have anything else like in our old tibble. It has some things that our text does not have, like URLs, hashtags, mentions. But you can see how this is very useful if you do have those in your data. What our data does have, though, how many times do people speak with first-person pronouns, second-person pronouns, number of words, number of unique words, number of lowercase characters, lowercase spaces, exclamation punctuation mark, commas, and so forth. So let us bind this with our original data frame, and then let's group by Ang versus everyone else, and then let's summarize. So we're going to say across starts with this n underscore. So we're going to summarize across all these things, and then take the mean like this. So this gives us, so for grouping by these two, we're going to say across, we said across all these different columns, I want the mean. I want the mean for all of these. So I really am enjoying using me across these days. It's making something so nice and smooth that I often struggled to do before. So that was great. So now this is wide, and so let's make it tidy, narrow, with pivot longer. So we're going to pivot, again, those starts with n underscore like this. And let's say names to, and let's call that text feature like this. All right. So this goes, so we can see here, so this is all Ang. Let's, what are we going to do here next? There's a bunch of zeros. Let's say we only want things that we want to that are not close to zero, like this. So that is looking good there. Okay, good. So some things are, of course, we counted up and then took a mean. So some of these things are low, and then some of these things are high. I'd like to make a visualization. First, let's just make a visualization with this as it is. Let us, let's put ang on the x-axis, value on the y-axis, say fill equals ang. Let's make little bar charts, lots of little bar charts. We're going to say position equals dodge. We're just going to have a whole bunch of them. And I don't think we'll need the legend. And we're going to facet all of these text features. And they will need to be scales equal free like this. Okay, so let's see how that works. All right, we are going to need, let's see how this worked. Okay, that worked pretty well. We're able to see, yes. Okay, so let's just clean this up a little bit more. Let's make, I think let's make one more column instead of 5, 6. And let's take, so let's remind ourselves, what are we saying? So we don't need that X one. And on the Y, this is the text features, mean text features per spoken line. And we will, I think we need to make it a avatar color again, right? Scale, fill, avatar. And let's use air nomads again, because we're still looking at like ang versus everyone else. All right, let's try this. Come on, you can do it. Okay. Okay. So, let's do one more thing. Let's reorder this. So text feature in order of value, like this, so that we can see the ones that are the highest up in the corner, and then it'll go down to the lowest. Okay, so ang speaks shorter lines than other people, but you can see that the proportion is different. He has more unique characters per line proportionally. You can see the number of exclamations per spoken line is higher. The number of first person, we saw that with I and I'm. So what we were going to try to do here is use these differences between ang and other characters, between these text features, like how is punctuation used, how are pronouns used, how are unique words or unique characters used to be able to tell the difference between a line that is spoken by Aang and a line that is spoken by someone else. So we have things like, first, second person pronouns, to be verbs, just the overall length of the lines. All of this, we're going to see which of these things, can we build a model that is able to distinguish between a line by Aang and a line by someone else using this kind of information. So let's do it. Let's see if we can do it. All right. That looks hideous. I can't look at it. Okay. So let's load the tidymodels framework set of packages for modeling in R. And the first thing we're going to do is we're going to do an initial split. So an initial split for using that avatar data that we have. We are going to do a stratified split so that we have the sampling happens in Aang and everyone else's lines. So let's call this avatar split. And then we will tab avatar training on avatar split, avatar testing on avatar split. And we need a seed for reproducibility. Okay, so our training data is here. We have about 7,500 lines. And let's remind I don't think we've actually looked at this yet. We do have some pretty significant class imbalance. There are many more lines spoken by people other than Aang than spoken by Aang. So that is something we are going to have to deal with. While we're here thinking about the data, let us make a set of resampled folds. Let's use let's create a set of cross-validation folds. So let's say we do this on the training data. Avatar train, and let's again do it with stratified sampling, especially now that we've noticed we have this this class imbalance, and let's call this avatar folds. And let's set a seed again, because that again is has randomness in how it is chosen. So each one of these folds is a like a simulated data set that we'll be able to use for training or choosing models. Now let's get ready to do our data preprocessing. So we're going to use a recipe for this. So we're going to say we want to predict Aang, whether it is spoken by Aang or not, using the text. So let's look at avatar train again. I don't think we're going to actually use book. I probably could have left that out. So we're going to do it Aang predicted by text. And the data here we're going to say is avatar train. So the reason we give the data here is so that the recipe knows the data types that it's dealing with. So let's load a couple of add-on packages that have extra recipe steps. First, let's do Themis, which has recipe steps for dealing with class imbalance. So for example, we're going to use step down sample on Aang. So this is just very simple. Where we're just going to downsample so that we're going to throw away basically a lot of this other data so that it's balanced. Believe it or not, sometimes throwing away a bunch of data can give you better results than keeping the data, so that we can build a model that can learn both the positive case and the negative case. If we did not do this, then we would build a model that largely learned how to learn things that were other. Next, let's load the text recipes package, because the text recipe package has a step text feature, and we are going to do text feature on the text column. So this, like if I load this right now, we're going to do text feature extraction. So if I look at step text feature, what it actually does is it just actually goes to the text features package and does all these count functions that we just talked about. So it does largely what we just showed, which is great because we can have this easily available to us in a pre-processing function, where we can do it within our cross-validation folds, within our modeling pipeline. Let's next do remove variables that have 0 variance. This is going to be nice because it's going to get rid of all of those columns for us, like all the URLs and things that we don't have any of. And then let's step normalize, because we're going to try to use at least one model that has that is sensitive to centering and scaling. So our we need to normalize, which centers and scales. While I'm here, let's prep the recipe and juice it, just so you can see what happened to it. If you're modeling using a workflow, which is what I'm about to show, we don't use the prepped recipe, but it can be helpful to understand what's happening. When you declare the recipe here, you're specifying it, saying what's going to happen, what you want to do, but you're not actually estimating, for example, which one of these observations am I going to keep and am I going to throw away? You're not finding out which of the predictors actually have 0 variance. You're not estimating the means and the variance here. That happens in prep. Okay, so we've got our data pre-processing going. A prep is where you could see when I defined the recipe, nothing was actually getting computed or estimated, but when I prepped it, that's when it happened. And then juice goes back into the prepped recipe and gets the data out that was used to the training data that was used to compute it. And so we can do that to see, oh yeah, like what actually happened? What did I get out at the end? How many, features do I have? And similar. So for example, if I wanted to understand which ones were getting removed, this isn't going to work because it's not going to be able to normalize things that are 0. Well, it can, I guess it will just have like NAND or something. I can juice and then it'll still have all these things about URLs and whatnot there. All right. Okay. Yes. Okay. So let's keep going and let's talk about the model. So let's do, let's try 2 models with some sensible defaults. Let's try a random forest model. Let's just make sure there's enough trees. And let's use the Ranger, whoopsie-daisy. Let's try the Ranger engine. And we are doing classification here. We're trying to say, did Aang speak this or not? And then let's try a support vector machine. So let's use the radial basis function. It's pretty flexible. And let's, you can tune, like with a random forest, you can tune these values like cost and these parameters here. But let's just set a default here and then and see what kind of results we get here without tuning, but with a default. So let's use Kern Lab for the engine. And again, we need to set the mode of classification, because these are both algorithms that can be used for classification or regression. And let's start avatar workflow. Let's start a workflow here. So we'll say workflow, and then let's add a recipe, our recipe here. And if we look at this recipe, notice that the workflow right now doesn't have a model. It has a preprocessor, but not a model. So what we're going to do next is we're going to take that sort of so a workflow is a way to put together pieces of your modeling, your modeling process, and they stick together like Lego blocks so that you can carry them around. And this, so this one right now has a preprocessor, but it doesn't have a model yet. So we're going to do that when we get ready to do the model fitting. So let's set up parallel processing here so that we don't have to sit and wait too long. So let's take the workflow and let's add the first model. And then we're going to do fit resamples. And here's what we need to add here. We need to add the folds that we made. Let's add some non-default metrics. We add a metric set. So we can keep in here the things that are the defaults, which are ROC and AUC and accuracy, but we can also add sensitivity and specificity. So we can understand better, do we do a better job predicting Eng versus not Eng? And then let's save the predictions. Control resamples. Let's say save prediction equals true. All right, so let's call this one RFRS like this, and let's set a seed like this. So let's get that one going, and then let's start another. While that's going, let's start another chunk down here for the support vector machine. So let's take this support vector machine specification, the model specification. Let's keep everything else the same, and then we'll make it SVM result like this. And everything else will stay, I don't know, let's change the seed just for kicks. Okay, so we have our random forest result. So we're going to be able to explore it a little bit. So we're going to be able to say collect metrics, RFRS, like so. And we're going to be able to say, so this will just give us the metrics. And then let's do a resampled confusion matrix like this. We just pass in the results. And we can do the same thing down here for our other result. Like so. Okay, so let's look at what we get. So first, the random forest. Okay, wow, impressive. This is not impressive, right? This is barely better than guessing. Barely better than guessing. I mean, it is better than guessing, right? Like we have evidence here that it is better than guessing, but barely. Also, the random forest is it does about as good a job between the positive and negative cases. Does not do a super better job on the positive versus the negative case. Is that right? Yeah, so here's the correct ones for Eng and the incorrect ones. So it's just, it does a little, it's okay. And then it's okay. And then the other way. So here's the correct other and the incorrect other. Okay, so let's look at the support vector machine. All right, so the ROC is higher and the sensitivity is higher, but the specificity is worse. And that's because the support vector machine does a slightly better job of identifying the positive cases, but at the expense of the negative cases. It is not the support. So comparing the random forest and the support vector machine here, the support vector machine is doing a better job of finding the Ang speaking at the expense of incorrectly finding Ang not speaking and saying Ang said that. Whereas the random forest is very close to just like, just barely not random guessing here. Okay, so this is pretty interesting, right? Like so first of all, there's, as you may have guessed when you looked at those example, spoken lines, there is just barely any signal here. Why am I showing you all this? I don't know. There's barely any signal here. We were barely able to learn anything from this delightful and fun data set. But the random forest learned, in this case, learned something different than the support vector machine did. If we, and depending how we tuned these models, it may shift around a little bit what kind of things they were able to. Depending on, your purpose, your business use case, your goals, you may have different needs around how your model behaves, like what your particular trade-offs are when faced with these kinds of different performing models. Let's move forward from here. I guess I should have. I guess I'm on to evaluating our model. So let's move this here. So let's because we haven't really done much with support vector machine models yet, let's take that and move forward. So first, to give you an idea of just how on the edge of just even meaningful this is, let's look at the predictions, and let's group by. So let's remind ourselves what that looks like. Let's get out the predictions. So this column is the true, who truly said it. This would give us the hard prediction, the hard class prediction, and then this is the predicted probability for each of the categories that we have. And so you can see, wow, they're so close to 0.5, like this is a situation that we're in. Okay, so we can make an ROC curve. We give it the truth. We give it the predicted probability for Ang, like this. And then we can plot that. So we can say ggplot, let's say 1 minus specificity, sensitivity, say color equals ID. Let's say line type equals 2. Oh, I don't know, is there like a dark brown? I forget. Because I don't know, have you ever seen an ROC curve done in the style of Avatar and the Last Airbender before? Because you're about to. That's what you get from watching this, because that's what we're about to do. Scale, color, avatar. I think it's time for Earth Kingdom. That's what I feel like. And it's nice to be able to do chord equal with what did I do wrong? Dark brown. I don't know what's a nice brown. I forget. I don't know all the GG plot. Okay. Oh my gosh, that brown is terrible. Oh gosh, the colors are so. We'll just make it black. Fine. Okay. Oh man, the black looks so bad. We'll just make it a little transparent. That covers a multitude of sins. Okay, so this this only has 9 colors, so we're missing one of our folds here. But you know, this gives you an idea of just the kind of performance that we're seeing with this support vector machine model. It is, except for that one resample, like it is on the side of the up above that dashed line. Like we do have some meaningful information in these text features, but barely. We are barely on the edge of being able to learn something meaningful in terms of Aang as a speaker from the model as we have set it up versus not. So please enjoy this Avatar: The Last Airbender themed ROC curve plot. Okay. All right. So one of the reasons I'm excited to do this model is because it gives us the opportunity to talk about variable importance in a new way. So we're going to use the VIP package for variable importance as we always do. It's a really great package. And we are going to, so let's start with that workflow we have. Let's add the model that we're using. SVM spec, and then we'll fit the model now to the training data, avatar train, and then we will pull out the we'll pull out the fit from it. And then after that, we are going to pipe it into this VI function. So the VIP package has several ways of computing variable importance scores. You can do it. There is such a thing as model-based importance scores. And so if you're doing something like GLMNet or a tree-based model, you use model-based importance scores typically because you like the model itself gives you something that helps you understand what is important to the model. Like in a linear model, it's the coefficients. In a tree-based model, you can look at all the trees and compute what's important to the model. For some models, like a support vector machine, we don't have model-based importance. And so then we have to go to some of these other options. Today, we're going to talk about how to use permutation model-based importance. So the way permutation model-based importance works is, hey, you have a model that, it's kind of like a black box, and you want to be able to understand what is driving the model to make predictions, at least on a global scale. So you permutation-based model variable importance, as the name indicates, permutes the variables, like leaves them out, shuffles them, and then based on that, says how much do the predictions change, and then is able to compute how important various variables are based on how the predictions change when you shuffle the variables. So that's how permutation-based variable importance works. So that's what we're going to do here. So this is different than how, at least I have shown how to do this in various videos and whatnot so far. So we do method equals permute, and since it's going to have to do a bunch of calculations, we have to really tell it a lot. We have to tell it, there's a bunch of stuff in here. There's a bunch of stuff in here. So you have to tell it the target, which means the Y, like the outcome. So in our case, that is Aang. You have to tell it the metric that you want it to use to compare. So we were using these. The VIP package calls AUC, not ROC, AUC. We have, pretty imbalanced, or we saw that difference there. So I don't think we should use accuracy. I think we should use AUC. We have to say a reference class. And to be honest, I always get this backwards. I think we want to say other, not ang here. If it comes out backwards, we'll say ang. The next thing we have to say is pred wrapper. And this is what are we going to use to do the predictions. So we could try to write a little wrapper, but we can actually just go to the underlying function and say, I want to use the predict method from KernLab. And then what is the training data? And the training data in this case, we actually want the juiced version here. Prep, sorry. Like this. We actually want this because we don't want, so avatar train just has the text. And we don't want it to say how important is text. That's like duh, that's the whole thing, right? That we gave it. We want to know how important are exclamations and how important are lowercase characters and whatnot. So we want the juiced data here. So if we do this, we can call this avatar importance. So if we do this one time, what it's going to do is, let's make sure it works. It will do it one time. So so we calculated the importance one time. It did one round of the permutation. But if we come up here and we say nsem, let's say 10, it will do it 10 rounds of the permutation. And as you can imagine, with a permutation-based calculation, we do in fact want them to do more than one time. Doing it one time is not a great idea. We want to do it a bunch of times. So while that is running, let's start setting up the visualization we want to make. So we're going to say variable equals, let's remove all that stuff. Here, text feature. Let's remove this. All right, it's done. Excellent. And let us variable fact reorder variable importance. Like so, and then we'll do this, ggplot AES, so importance on the x-axis, variable on the y-axis, color equals variable. So now we're not going to have just one value. We actually will have a measure of the center and the spread, so a standard deviation there. So we can do the points. Let's make them big. And we also can add in some error bars underneath it. So we can say, let's say x min importance minus x max importance plus, and okay, let's get rid of the whole theme. I mean the whole legend. All right, this is looking good. We do not need that y axis, and what we do, however, I think need some colors. Some avatar colors. Let's use Fire Nation here to end. oh, there's only 8 colors. Well, let's only take the 8 most important things. So slice max importance n equals 8. All right, what are the 8 most important things in predicting whether a line is spoken by Ang or not? So the number of capital characters, punctuation, extra spaces, exclamation points, lowercase unique characters. So by far, it looks like the most important thing is capitalization, and followed by these like punctuation and extra spaces, and then exclamation. So these are the things that we do see as important. So this model is this model shows that there's barely anything to be learned from these text features, and we also see that these error bars are very wide, right? But what we can, the differences that we see are the most important things that do contribute to the difference are these capitalization and punctuation and exclamations.
Well, that's certainly not the best performing model I have ever built in my life, but that's what happens sometimes, you know. This data is really fun. I'm really glad that I got to deal with it, but I think that's just how informative these individual lines are in terms of how predictive it is for who spoke the line. We were able to build both a random forest model and a support vector machine model, and then we walk through how we can compute variable importance, even for kinds of models that don't have underlying methods for model-based variable importance. And this time we went about doing it using a permutation method. So I hope this was helpful, and I will see you next time when maybe we'll build a model that does a little better.